Chapter 10 of History of Chemistry, Volume 2, by Sir Edward Thorp. This LibriVox recording is in the public domain. Organic synthesis, condensation, the synthesis of vital products. In its widest sense, the term synthesis, as used in organic chemistry, means the building up of carbon compounds, either from their constituent elements or from groups of differently constituted molecules. At one period, this term was confined to cases in which the organic compound was prepared from inorganic materials or from combinations which themselves could be formed from their elements, but latterly it has lost, in large measure, this restricted signification. At the same time, the attempt has been made to indicate by special terms certain classes of synthetical reactions. Thus, the special case of the formation of an organic compound by the union of two, or it may be more, molecular groupings is now frequently spoken of as condensation. Organic chemistry has been largely developed by the discovery from time to time of special reagents and special types of reactions which have shown themselves to be capable of extensive application. Such, for example, was Franklin's discovery in 1852 of zinc ethyl, the first of the organometallic compounds and the type of a series of substances of great theoretical importance and of great practical value by reason of their reactive powers. They led to the synthesis of the paraffins, the secondary and tertiary alcohols and ketones. A few years later, Wurtz introduced the use of metallic sodium as a condensing agent, and showed thereby how the hydrocarbon butane could be produced from ethyl iodide. 2 equivalents of ethyl iodide, C2H5I, plus 2 equivalents of sodium, Na, equals 1 equivalent of butane, C4H10, plus 2 equivalents of sodium iodide, NaI. Use was made of the same agent by Fiddick in 1863 in effecting the synthesis of the homologues of benzene by the action of an alkyl iodide upon bromobenzene. 1 equivalent of bromobenzene, C6H5Br, plus 1 equivalent of methyl iodide, CH3I, plus 2 equivalents of sodium, Na, equals 1 equivalent of toluene, C6H5CH3, plus 1 equivalent of sodium iodide, NaI, plus 1 equivalent of sodium bromide, NaBr. In like manner, Kekule in 1866 obtained benzoic acid by the action of carbon dioxide upon bromobenzene. 1 equivalent of bromobenzene, C6H5Br, plus 1 equivalent of carbon dioxide, CO2, plus 2 equivalents of sodium, Na, equals 1 equivalent of sodium benzoate, C6H5COONA, plus 1 equivalent of sodium bromide, NaBr. The readiness with which magnesium can now be obtained, mainly as a result of Sonstad's efforts to develop its metallurgy, has led to its application at the suggestion of Barbier in 1899 in place of zinc. The particular form of magnesium compound now employed as a reagent was prepared by Grignard in 1900 and is known by his name. It is obtained by bringing an ethereal solution of an alkyl iodide or bromide into contact with magnesium when the metal is dissolved, forming, in the case of methyl iodide, methyl magnesium iodide etherate, MgCH3I, parentheses, C2H5N parentheses 2O. Grignard's reagent has shown itself to be extraordinarily reactive, and a great number of condensations of hydrocarbons, alcohols, aldehydes, acids, ketones, amides, and additive compounds have been effected by means of it. Other condensing reagents of value are acetoacetic ester, sodium amalgam, sodamide, sodium ethoxide, dimethyl sulfate, zinc chloride, aluminum chloride, fused caustic potash, hydrogen chloride, phenylhydrazine, hydrogen peroxide in presence of a ferrous salt, Fenton's reagent, ammonia, and various amines. The application of these reagents has led to the discovery of a variety of new compounds, the mode of origin of which has served to elucidate their constitution. The great majority of organic syntheses, especially when they start by the use of inorganic materials, consist in passing from simple to complex molecular groupings by condensation processes. An interesting example of the reverse process is seen in the production of carbon suboxide or carbon carbonyl, C3O2, obtained from various malonyl compounds, but most conveniently prepared by the action of phosphoric oxide on malonic acid under diminished pressure, or by treating an ethereal solution of dibromomalonyl chloride with zinc. 1. Malonic acid CH2 (COOH N 2) goes to 2 water H2O plus 1 carbon carbonyl C CO N 2. 2. Dibromomalonyl chloride CBr2 COCl N 2 plus 2 equivalents of zinc goes to 1 equivalent of zinc chloride ZnCl2 plus 1 equivalent of zinc bromide ZnBr2 plus 1 equivalent of carbon carbonyl C CO N 2. Carbon suboxide is a colorless, extremely mobile, refractive poisonous liquid of specific gravity 1.11 with a strong and peculiar smell. It boils at 7 degrees and freezes at -107 degrees. It is stable only at low temperatures. At ordinary temperatures it polymerizes to a red solid, which dissolves in water, forming a solution of the color of eosin. The change is almost instantaneous at 100 degrees. Carbon suboxide is inflammable, burning with a blue but smoky flame. 1 equivalent of carbon carbonyl C3O2 plus 2 equivalents of oxygen O2 equals 3 equivalents of carbon dioxide CO2. Its low boiling point and the high value of its molecular refraction and dispersion, its general resemblance to the metallic carbonyls and ketones, etc., indicate that this remarkable oxide of carbon is, in all probability, the anhydride of malonic acid. Indeed, by the action of water upon it, it is reconverted into malonic acid. In point of principle, and viewed as chemical operations, the synthesis of vital products is in no wise different from the synthesis of any other group of organic compounds, and the special interest and even astonishment at one time created by the artificial preparation of such products have largely died away. The synthetical production of some of the substances formerly known only to be formed by vital action, either in the animal or the plant, has already been incidentally referred to. But it may be convenient to treat the subject of the artificial production of this group of bodies rather more comprehensively and as a subsection of this chapter on organic synthesis, since their formation by such means constitutes a phase in the development of chemistry, and has undoubtedly exercised a profound influence on scientific thought and on philosophical and even theological doctrine. During the past 50 or 60 years, the chemist has been enabled to form the active principles or characteristic products of many plants and animals. He has built up substances which were formerly regarded as capable of being made only by the very process of living. He has prepared compounds which were at one time considered as only producible by changes in organized matter after death. Since the date of Wohler's epoch-making discovery, already referred to in Volume 1, page 128, urea has been synthetically prepared by many reactions, notably by Regnault and Nathanson, by the action of ammonia on carbonyl chloride, and by Bassereau and Dexter from ammonium carbamate. Both these substances can be formed directly or indirectly from their elements. It may also be obtained by the hydrolysis of lead cyanate. 1 equivalent of lead cyanate, Pb (CnO) plus 2 equivalents of water, H2O, equals 1 equivalent of lead carbonate, PbCO3, plus 1 equivalent of urea, CO (NH2) and 2. The successive steps in its production from inorganic materials by this method are: potassium plus carbon plus nitrogen goes to potassium cyanide, KCN, goes to potassium isocyanate, KCNO, goes to lead isocyanate, Pb (CnO) and 2, goes to urea, CO (NH2) and 2. Associated with urea as products of metabolism are uric acid, xanthine, and sarcine. Urea was first artificially transformed into uric acid by Horbaczewski, and its synthesis was effected by Behrend and Rosen. Closely related in chemical composition to these substances are theobromine and caffeine, the characteristic principles respectively of cocoa, the fruit of Theobroma cacao, and of coffee, tea, mate, the leaves of Ilex paraguayensis, guarana, obtained from the seeds of the South American plant Polonina sorbilis, and the kola nut of Central Africa. Strecker in 1860 showed how theobromine may be converted into caffeine, and Emil Fischer by similar means transformed xanthine into theobromine. Since that time xanthine itself has been prepared artificially. Caffeine can now be built up from its elements by a series of transformations effected by a succession of chemists as follows. 1. Carbon and oxygen give carbonic oxide. Priestley, Cruikshank. 2. Carbonic oxide and chlorine give carbonyl chloride. J. Davy. 3. Carbonyl chloride and ammonia give urea. Nathanson. 4. Urea gives uric acid. Horbaczewski, Behrend, and Rusin. 5. Uric acid gives xanthine. E. Fischer. 6. Xanthine gives theobromine. Strecker. 7. Theobromine gives caffeine. E. Fischer. Synthetic theobromine is now made on the large scale and introduced as a soda compound in combination with sodium acetate into medicine as a diuretic under the name agurin. Synthetic caffeine is also prepared on a manufacturing scale from uric acid through the medium of the methylxanthines. The close relationship of xanthine to uric acid is of great physiological significance, since there is little doubt that the xanthine bases are the most important sources of uric acid within the organism. In this connection, reference may be made to the large number of synthetic organic products which have been introduced into medicine during the past few years. The investigation of the constitution of the alkaloids has served to show in many cases to what particular molecular grouping the physiological action of the drug is mainly due, and this has led to the production of substances containing these groups, but not necessarily existing as natural products. Among these may be mentioned antipyrin, a derivative of the pyrazole group, discovered by Knorr in 1883, and of which upwards of 17,000 kilos of the approximate value of 35,000 pounds were produced in 1899. This substance is a phenyl dimethyl pyrazolone. Acetanilide, C6H5NHCOCH3, an aniline derivative, was discovered by Gerhardt in 1853. Phenacetin is a derivative of para-aminophenol, which consists of a benzene ring substituted as follows. Carbon 1 bears an ethoxy group, OC2H5. Carbons 2 and 3 bear hydrogen. Carbon 4 bears the acetamide group, NHCOCH3. And carbons 5 and 6 bear hydrogen. An extraordinary number of synthetical soporifics have been introduced at various times during recent years. For example, chloral hydrate, veronal, sulfonal, trional, and tetranal, etc. The three last named substances are closely related, as the following formulae indicate. The structure of sulfonal consists of a carbon atom substituted with two ethyl sulfonyl SO2C2H5 groups and two methyl CH3 groups. In trional, one of the methyl groups is replaced by an ethyl C2H5 group, and in tetranal, both methyl groups are replaced by ethyl groups. Sulfonal is prepared by the oxidation of a substance obtained by the combination of acetone and ethyl mercaptan. Veronal is an ethyl compound of barbituric acid obtained by the condensation of urea and diethyl malonyl chloride. The structure of veronal is a six-membered ring, C double bond O, NH, C double bond O, NH, C double bond O, C, parentheses C2H5 Attempts have been made to connect the physiological working of local anesthetics with particular constitutional groupings, as for example in cocaine, and these have led to the introduction of such substances as the orthoforms nervanine, stovaine, allicine, novocaine, and adrenaline into medicine. Adrenaline, used in connection with cocaine, has proved itself a most valuable agent in producing what is called lumbal anesthesia, whereby large sections of the lower half of the body may be rendered completely insensitive to pain. The study of the putrefactive changes of albuminous substances of animal origin, induced by the activity of microorganisms, has revealed the existence of a number of basic nitrogenous compounds, some of which are highly poisonous. These were classed by Selmy under the generic name of ptomaines, from the Greek ptoma, for a corpse. Brieger found that the typhoid bacillus yielded a poisonous substance, typhotoxine, and that the bacillus of tetanus forms a highly toxic basic body, titanine. All the ptomaines, however, are not poisonous. Some of them, like choline, from the Greek choli, for bile, originally discovered by Strecker in bile, in the brain, in yolk of egg, and now found to be among the products of the putrefaction of meat and fish, have been known for some time past. Choline was first synthetically prepared by Wurtz. Neurine, from the Greek nevron, for nerve, a derivative of brain substance, is related to choline and is readily transformed into it, but differs from it in being very poisonous. It has been synthesized by Hoffmann and Bayer. Another of the so-called corpse alkaloids, cadaverine, has been synthetically formed by Ladenburg. Schmiedeberg and Kopp isolated the poisonous principle of the fungus Agaricus muscarius, which they called muscarine. It occurs with choline, from which it can be readily obtained, among the products of the putrefaction of flesh, as well as in many fungi. The synthesis of the alkaloids conine, atropine, cocaine, piperine, and nicotine has been already referred to, on page 105, as also that of vanillin, the aromatic principle of the dried fermented pods of certain orchids; coumarin, the odoriferous principle of woodruff and of the tonka bean; of salicylic acid, oil of wintergreen, oil of mustard, bitter almond oil, and camphor. Acetic, succinic, tartaric, and citric acids have also been artificially obtained, and may indeed be built up from their elements. No synthesis of recent years created more widespread interest than that of alizarin, first effected by Grebe and Liebermann in 1868. Its successful commercial manufacture by Sir William Perkin in this country, and by Caro in Germany, created nothing less than a revolution in one of our leading industries, and completely destroyed a staple trade of France, Holland, Italy, and Turkey. To procure alizarin, anthraquinone is treated with sulfuric acid, and the product is fused with alkali and potassium chlorate. The remarkable industrial results attending the synthetical formation of this matter product naturally led to attempts to procure other important vegetable dyestuffs artificially, notably indigo. The synthetical production of indigo has been accomplished by the joint labors of many chemists, notably Bayer, Heumann, and Heymann, and the substance is now prepared on an industrial scale. The starting point is naphthalene, obtained from coal tar. This is converted into phthalic acid, which is then transformed into thalamid. The last named substance is converted into anthranilic acid, which on treatment with monochloroacetic acid is changed into phenoglycine orthocarbonic acid. On melting this with caustic potash, it yields indoxyl acid, which is transformed into indoxyl and thence into indigo. Another method is to treat the sodium salt of phenoglycine with sodamid, whereby indoxyl is at once obtained, and this by condensation yields indigo blue. One equivalent of the sodium salt of N-phenoglycine, C6H5NH CH2CO2Na, plus one equivalent of sodamid, NaNH2, goes to indoxyl, in which the carbonyl of the N-phenoglycine has cyclized back onto the carbon of the benzene ring adjacent to the carbon bearing the nitrogen, to form a fused 6,5 ring system. Indoxyl, in turn, is then dimerized to form indigo blue, which consists of two molecules of indoxyl joined by a carbon-carbon double bond between the two carbons which were formerly the CH2s, situated between the carbonyl CO and the NH in the 5-membered ring of indoxyl. Phenoglycine is obtained by the action of monochloroacetic acid on aniline, which in its turn is obtained through nitrobenzene from benzene. Since benzene can be synthetically prepared by the condensation of acetylene, which can be obtained by the direct union of carbon and hydrogen at a high temperature, it is theoretically possible to build up indigo blue from inorganic materials. Synthetical indigo blue was placed on the market in 1897 with an almost immediate effect on the production and price of the natural variety, and today the output of Bengal indigo has fallen by more than 50%. In 1902 the amount of the natural product was probably not greater than 3 million kilos, whereas in the same year the production of synthetic indigo was upwards of 5 million kilos. Before the introduction of the artificial variety, the price of pure indigo blue ranged from 16 to 20 shillings per kilo. By the end of 1905 it had fallen to 7 or 8 shillings. Mention should be made also of thioindigo red and the thionapthine derivatives, some of which promise to be important coloring matters. In recent years the so-called sulfur coloring matters have acquired considerable importance. Space will not permit of any fuller treatment of the development of the manufacture of the artificial organic coloring matters. This industry had its beginnings in England, but it is now mainly carried on in Germany. Its importance may be gleaned from the fact that the value of the production at the present time amounts to not less than £12,500,000 per annum, 2/3 of the output being exported. It demands the services of battalions of skilled chemists, and gives employment to many thousands of artisans. Some of the most notable achievements of modern synthetical chemistry are to be found in the work of Emil Fischer on the sugars and the proteins. Although the sugars have from the earliest times been reckoned among the most characteristic products of plant life, and have long been used as food and as sources of alcohol, comparatively little was known until lately of their real nature and mutual relations, in spite of numerous attempts to elucidate their constitution. Much of the mystery surrounding their chemical history has now been dispelled. Not only has the molecular structure of the more important naturally occurring sugars been unravelled, but a large number of hitherto unknown members of the various groups of the great family to which they belong have been prepared. The first insight into the constitution of these bodies may be said to date from the researches of Kiliani, made about a quarter of a century ago. In 1887 Fischer effected the synthesis of a form of fructose, fruit sugar, and immediately afterwards of ordinary dextroglucose, grape sugar, and its enantiomorph, levoglucose, and the two optically active forms of natural fruit sugar. Since that time such sugars as arabinose, xylose, fucose, mannose, sorbose, cane sugar, maltose, lactose, etc., and the sugars existing as glucosides have been examined, their stereochemical relations defined, and synthetic methods of production devised. Incidentally, their behavior towards enzymes has been studied, and the remarkable selective action of these ferments on the various groups, due apparently to differences of configuration, has been established, with the result that much light has been thrown on the mechanism of enzyme action and on the general theory of fermentation. The study of the proteins by Fischer constitutes a new chapter in biochemistry. Although long recognized as among the most important of vital products, from the circumstance that they enter into the composition of animal tissues and secretions and are essential constituents of protoplasm, the proteins are among the worst defined substances known to the chemist. They are difficult to separate, as they closely resemble one another and afford no certain indications of individuality. Very few of them have been obtained in a form in which their identity could be established. Oxyhemoglobin was isolated some years ago, but the proteins of serum albumin and of egg albumin have only recently been obtained in definite crystalline shape. All the proteins, even the simplest of them, are of great complexity and possess apparently very high molecular weights. Hemoglobin, for example, appears to have approximately the formula carbon 158, hydrogen 123, nitrogen 195, oxygen 218, iron 1, sulfur 3, with a minimum molecular weight of 16,600. Indeed, there is experimental evidence to show that it is even considerably higher than this. The main clues to the nature of these substances have been gained by the systematic study of their hydrolysis, induced by reagents or by the action of enzymes, whereby they are found to break down into proteoses, peptones, and a great variety of amino acids, some of which have been synthesized. Among the proteins of simplest constitution are the protamines, found in the spermatozoa of fish. They are basic substances, especially rich in nitrogen, forming salts with platinum chloride and certain metallic oxides. The best investigated member of the group is salmine, obtained from the testicle of the salmon. The products of its hydrolysis have been fairly well ascertained, and their quantitative relation is such that the substance must have at least a molecular weight of 2045, corresponding to the formula carbon 81, hydrogen 155, nitrogen 45, oxygen 18. Many of the albumins and globulins, coagulable proteins contained in the animal tissues, have been isolated in a more or less definite form, and some of them have been found to yield substances akin to carbohydrates. Thyroglobulin, the globulin of the thyroid gland, has been found to contain iodine, apparently as a normal constituent of a body which can be isolated as a definite proximate principle. The presence of this element is possibly connected with the curative value of the globulin in creatinism. A considerable amount of work on the vegetable albumins has also been done of late years, and some of them, as edestin from hemp seed and cein from maize, have been obtained in definite form. The limits of this work preclude a more detailed account of one of the most interesting but at the same time one of the most obscure departments of chemistry. The field has hitherto been tilled in a somewhat intermittent and partial manner. Now that it has been entered by chemists of experience and resourcefulness, armed with modern methods of cultivation, it will doubtless soon yield a rich harvest of facts, valuable alike to the physiologist and the physician. There can be no reasonable doubt that the chemical processes of organic life are essentially similar to those of the laboratory. The doctrine that a special vital force is concerned in the production of vital products receives no support from the teaching of modern science, and is, indeed, contradicted by it. At the same time, it must be admitted that we know very little as yet of the real agencies at work in the elaboration and mutations of chemical products in the living organism. Because we have effected the putting together of such a product by purely laboratory processes, it may be, indeed, by a variety of different and dissimilar processes. It by no means follows that any one of them is identical with that actually occurring in nature. The building up of materials in the plant by the agency of light, for example, has not yet been imitated in the laboratory. Many plant products are produced by the action of unorganized ferments, so-called enzymes, none of which the chemist has succeeded in creating. Processes akin to condensation undoubtedly occur in the living organism, but the means by which they are effected are, in all probability, very different from anything known to the chemist at present. Many laboratory condensations are only accomplished at relatively high temperatures or under considerable pressure, or, in other words, under totally different conditions from those which obtain in the organism. End of chapter 10.